All right, welcome to non-destructive testing. This is actually a pretty fun subject matter, in my opinion, at least. So non-destructive testing essentially is a way for us to inspect specifically like structures, hardware, like aircraft structure, and it doesn't require any kind of breakdown or tear down. Typically, it's usually something that you're going to be able to just walk up to the airplane and do without a whole lot of drama. Now there are some times that you'll have to do that. And we'll get into a little bit of that. All right, so inspection basics. So let's just go over the why behind inspections. There are tons of stories of aircraft that fell out of the sky because of a structure's failure. They were just flying along, and then all of a sudden something happened, and they don't know. Personal story on one of these on the OH-58. They had beefed up. They had to beef up the tail rotor gearbox. So, due to the way that they had modded the Delta model of the OH-58. There was a lot of extra strain and stress put on the tail rotor. Just because of anything like a big, like you put a lot of extra gear on the aircraft, it has to generate more lift, has to work harder. That means the main rotor is going around faster and faster and faster with more torque. So in order to counteract that, you have to beef up the tail rotor on the back. Well, the empennage the tail boom that tail rotor gearbox is mounted to is only really built for so much force. Well, whenever they beefed that thing up, it put a lot of extra strain on the mounting bolts for that tail rotor gearbox. And so what was happening is that we would get these hairline cracks that would come off of there. Well, a lot of this stuff is all just kind of like academic until you actually see it in real life. And so we would go out and we would inspect these things on a regular basis. Every 10 hours we're looking at it. During pre-flight one time, I walk out to it, and keep in mind, we've looked at this thing every 10 hours for a pretty good long stretch of time, because this was in the middle of the surge in Baghdad. So like we've been flying lots of hours for an extended period of time. And so I walk out there and I grab the shaft, the tail rotor output shaft, and I pick up on it just like normally. Usually the whole aircraft like lurches forward because it's bolted in. Well, this time it didn't. The whole gearbox just like picked up, and I was like, well, that's probably not good. And I looked down at it, and right where that inspection plate was, it finally cracked through and finally just gave way. And we ended up having to replace the whole tail section of the aircraft. But on the NDT side of it, that was a place that we always did visual and then eddy current inspections every so often. And so the reason why we do these things is because aircraft have fallen in the past, and we don't want any structures failures killing anybody. And so it's something to take really, really seriously. And so the way that's the overview, that's the why behind we do these types of inspections. When do we know we're supposed to do these things? Well, aircraft is expensive and it comes with instructions. It'll tell you when you're supposed to do these things. So you have two basic kind of times that you're going to do NDTs. One is required regular scheduled inspections, and the other one's going to be on condition inspections. So let's talk about the regularly scheduled inspections. Regularly scheduled inspections are always going to be broken down into, depending on what inspection program you're in, and we'll get into that here in the next couple of videos of inspection programs and how they're all broke down. But essentially, it will tell you, it'll say like, hey, look, every so many hours, or every C check, or every annual, or whatever, like the inspection requirements in the maintenance manual will tell you, like, this is the frequency in which you're going to do these things. And it's going to say like, hey, look, this is the area, and it'll usually give you kind of like a description. Stick with the 58 because I know it. It'll say like, front left, tail rotor gearbox mounting bolt, and like it'll say something like in adjoining areas, or areas in proximation. For us, the engineers just simply put an inspection plate there. So there was like an area that had like polished aluminum that no paint went on. So you'd look at the tail boom and it'd be all painted up and super like that Carg paint. It's kind of has Army helicopter color, and then also there's this big silver plate, and that's where the inspection was at, so that way we could see any deformities really easily. So the maintenance manual basically tells you what to do and when to do it, and that's something that you just need to be familiar with. That when we start inspecting aircraft, you're gonna the first thing you do is sit down and read. Like you're gonna read and understand exactly where you're going, what you're doing, and try to get your plan of attack, and then go and do the inspection. You don't just tear into it. The other one is on condition. So before we get on condition, it'll also tell you how to inspect it. It'll say hey, visual inspection, eddy current, mag particle, whatever the inspection requirement is, it'll dictate to you how you're going to do it. So on the 58, we would do visual inspections every PMS, which is every 10 hours, and then every I think it was every 25 hours or something like that. We would have a mag particle come. So we would call the structures guys. They would come out with their eddy current machine, and they would do the whole eddy current thing, and they would find any sort of defects in there, and we did find some over time, and we ended up having to replace tail booms over that, which ultimately is what killed the 58. Well, one of the things that killed the 58. So that's the kind of puts a cap on the required. Now, the on condition inspections. So throughout an aircraft inspection program, you're going to be going and it'll tell you to look for things. So it'll say something like on my airplane, it's it says inspect the floor for any non-conformities or damage or whatever. So on my airplane in particular, you have an aluminum base floor that you just you're looking for corrosion, you're doing a visual inspection. All right, and then it has these stretches of composite where the floor is built up. I have no idea why. And so on that, you'll do a tap test. And so you look at it and you look to see, hey, look, is there anything that's just visibly wrong with it? Does it have a gaping hole in it or whatever? And if you don't see that, then it's okay, you start tapping. And we'll demo a tap test and how you go about doing a tap test here in a little bit. And so let's say you're looking at that and you find something that just looks weird. You're like, man, this isn't right. Or you see you're tapping and you hear a void and you're like, maybe that's something. That's when you send out for NDT. Now, depending on what your shop's capabilities are and what you have available, you can kind of tailor that NDT to it. If you're a GA mechanic and all you have, you're operating on a shoestring budget and you're looking at something that's metal, you're probably going to be doing a dye penetrate test. And we'll demo that here in a little bit. And so you're going to take your little cans, spray it on there, let it set, and then come back with your flashlight, your magnifying glass, and try to see if you see any cracks anywhere. So that's an option. If you're on the flight line and written at Boeing, then you call up the NDT line and say, hey, look, we have a problem. We think we have a void in a composite structure. Can you send out the ultrasonic guys? They'll come out with their ultrasonic tester and they'll say, oh, yep, there's a void right there, and they'll actually do the inspection. And we'll get into what all these are here in just a minute. But so just know that your job as the frontline mechanic is to go over there and do the inspection and do it really, really well, because you're the one that's actually going to find stuff. Everything else is just there to confirm the thing that you found. And so you have to be really, 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 really good and really, really meticulous about the way that you inspect things. The first set of tools that you use are just simply your eyes. You just look at the thing, and you'll start to, over time, you'll start to say oh yeah, I've seen this before, I've seen that before, whatever. And so it's a really good thing to partner up wherever you go with somebody who's a really good inspector, who's somebody who finds stuff on a regular basis. Learn from that guy, because he's got to figure it out, and try to emulate anything that he does. The more that you can see, and the more weird stuff that you can see, the better off you're going to be in the long term because you're going to end up seeing, like, you're just going to get reps in, and you're going to see all the combinations of weird things that airplanes will end up doing. Find a void in a composite structure one time, and you'll find voids the rest of your life because you'll know exactly what you're looking for. Right now, it's like there's a void, and we're going to do a tap test, and we're gonna try to emulate that as best that we can in class, and then you're going to do a bunch of composite work throughout the whole coursework. But like, it won't be until you find your first real true void that you know exactly what you're looking for at that point. You're like, okay, like, now I get it. Um, Same thing with metals and stuff. Like, you'll start to get a sense of, like, this is not an area that, like, you generally will find problems. You'll start to get a sense of, like, okay, this bend here, or like, you'll look at structure and you'll say, like, okay, well, there's a lot going on here. I can kind of almost feel the stress the airplane's going on whenever I look at this one area, and then this one area looks really, really bad, and you'll want to pay a lot of attention to it. And that just comes with experience, just doing it a lot. Okay, so anytime you want to inspect any things, two other tools that you need, maybe a third one. The first one is you need to have a rag. Always, always, always clean to inspect. And so if it says inspect something, think in your brain, like, inspect means to clean. It means to take a shop towel and go over it and make sure that it's clean. You can always tell, like, an aircraft that's not been inspected thoroughly and not been looked at, if it's just gunky and grimy and dirty. Because anywhere that you, the mechanic, should have gone and inspected, you should have taken your shop towel with it and cleaned off all the junk that could hide any kind of defect. I have found untold amounts of problems and stuff simply by cleaning up. Like, it says, like, hey, look, inspect this area. You go in there and you get all the dirt and all the grime and all the just junk off of it, and you'll end up finding cracks, you'll end up finding working rivets, you'll find voids, you'll find all manner of things simply by cleaning. So always have your shop towel. That's like your primary inspection tool, is just simply making sure that whatever it is you're looking at is clean. The next one that you're going to use is your flashlight. Using a flashlight to inspect is almost an art. You'll know, like, if you hang out around airports and stuff, and you see like a GA shop that's like really, really busy, and there's a lot of like just like rock star mechanics there. You'll see a lot of these guys walking around with like $200 Streamlights in their back pocket. And the question is, why? Like, why do they do this? And it's because those Streamlights are super, super, super bright, and they've learned how to, like, look down a rivet line with their flashlight to see, like, if there's anything that's going on weird, or look down a wing and see if there's any buckling or whatever. And you'll start to see, like, as those internal failures happen, it causes the surface of the wing to contort and get weird, and it'll cause waves, and those waves cast shadows whenever you shoot a light down it. If you can't see it, you can't inspect it. So you need to have a good flashlight to be able to see into like dark areas. And there's a lot of like these like weirdo places that you'll be required to go on and inspect. You have to do it. Like on my plane, like, you have to pull out the back firewall and look down the tail boom or the empennage of the airplane. And so, like, if you don't have a flashlight in there, you're not really, you can look down and you can see it, you can check the box and do the visual inspection, but you're not really inspecting anything if it's all dark. So you really need to have a flashlight. A flashlight can also, like, will shine through. Like, if you have a buddy on the outside and you're like, hey, look, I feel like there's something not right here, and you shine a light onto it, and he sees light coming from the inside outside of the aircraft, then you know that hey, look, there's a problem there. There's a crack, there's a rivets falling out, or whatever the thing is. So always have a flashlight on you. The flashlight is probably your biggest early warning system that, hey, look, there's a problem. We need to NDT this. We need to like kind of elevate this issue, whatever it is. And the other one is an inspection mirror. I mean, it's in the name, inspection. You're going to take that mirror and be able to get into places that you otherwise couldn't. In the same kind of vein, as your phone is actually really, really, really useful. So, like, you take your phone and you can get in places and take pictures of things, and then come back and look at the picture, then all of a sudden you can see a lot. It also has a flashlight built into it. So whereas the modern cell phone might have corroded a lot of things, or a lot of parts of American society, just by the distraction and stuff, it has enhanced our inspection technique. It's a good tool to use for that. I mean, you can use it like a mirror. You can put the camera on and look, put it on the backside, and use that camera to like show what's going on in your phone. So be creative with the way that you inspect things, and always think that especially with helicopters, helicopters trying to kill you, and so it's a constant war of trying to keep that thing flying, because it doesn't want to fly and wants to come to pieces. Airplanes are not nearly as aggressive as helicopters are, but they're machines, and they are prone to failure. Like, everything is in a state of entropy, for lack of better terms. It's every time you crank it, every day that it sits out on the flight line, it's slowly degrading, and your job is to find where it's degrading the most and then fix it and get ahead of it. And NDT is one way that we go about doing that. Let's go over our different methods of NDT with their advantages and disadvantages. Okay, first type of inspection, or these are, I keep saying NDT, NDI, so non-destructive test versus non-destructive inspection. So these are going to be NDI methods, non-destructive inspection methods. All right, so first is visual, all right? So visual, like we've talked about, is just your eyes. So they're inexpensive, highly portable, immediate results. You don't need a lot of training, and there's no preparation for it. If you can see it, you can look at it. You walk up and visually inspect the outside of the aircraft. If there's a gaping hole in it, then, hey, look, that's probably not right. I'm pretty sure my grandmother could walk out to an airplane and look at it and say, like, hey, look, the hole in the side of the wing is probably not supposed to be there. So that's the advantage of it. Now, the disadvantage of a visual inspection are just that there's surface discontinuities only. Like, you don't have X-ray vision unless you're Superman, and you can't see what's going on the inside. And this is especially important for composites, because composites generally fail internally. They don't necessarily fail externally. Whereas a lot of corrosion and other types of failures that you'll get with especially with ferrous metals, you'll get exterior failures before you get interior failures. And so, like, you can see those, whereas you can't see composite stuff. So that's something to take in consideration whenever especially with more and more airplanes going to composites. They generally only large discontinuities. You can't see, like, you don't have a microscope attached to your head looking at things. And a lot of these failures, for a long time, they'll be really, really, really small. And also, one day they get really, really, really big. And so NDT allows us to find them whenever they're still small before they cause some sort of damage or some sort of fatality. And then misinterpretation of scratches. This is a big one. So a lot of times you'll find scratches on things, and you'll end up having to call out for some sort of NDT because you can't 100% for sure know that it's just a surface scratch and it's not like a crack that's worked its way to the surface. There's ways that you can do that by running your thumbnail over, and if it catches, it's probably more than just a regular scratch. But even that is somewhat, not reliable. And to be certain, especially if it's a safety of flight issue, you're going to have to elevate the way that you're doing the inspection, even if it's just a dye penetrant type of thing. All right. So our next method is dye penetrance. All right. So we're going to demo this. But it is portable, inexpensive, sensitive to very small discontinuities, 30 minutes or less to accomplish a minimum skill required. You'll see how easy it actually is, and the fact that you can, take all of it and, get it for less than $50, like the whole thing off the internet. And you can put it all into a little tool bag and carry it wherever you go. It's no big deal to whip out some dye pen cans and spray this stuff down and make sure that the scratch or whatever failure it is that you've identified isn't something serious. That's just hey, look, it's just a surface discontinuity, not something super crazy. But it has its limitations. So its disadvantages are you can only locate surface defects. Rough or porous surfaces interfere with the test. So cart paint on the helicopter, like we were talking about, does not do well with dye penetrant. Part preparation required, so your removal of finishes, sealant stuff. So if you think that you have an area that has a crack that's working, and you're going to dye pin it. Well, you're going to have to remove all the paint and it becomes like this whole thing to prep the surface before you can spray the dye pin on there. And there's other inspection methods. You don't have to do all that. So it's not only you're saving a lot of time and money, you're also not like anytime you touch an airplane, you run a risk of damaging an airplane. And so like whenever you start taking like MEK or and some sanding paper to it to prep the surface, you may be doing more damage, especially if you find out that like, hey, look, there's nothing wrong with it. You might actually have damaged the aircraft by inspecting the aircraft, and so you don't want to do that. So there's that limitation with dye pin. A high degree of cleanliness is required. So you'll see that we have to like really clean the surface before we start spraying our dye pin chemicals on it. The reason being is that the way that the way that the inspection operates is it's looking to see if the two chemicals come together at a certain point, and they will emit they'll reflect a different what's the right way to say it? It'll reflect a different color whenever you shine the black light on there. And so whenever if you have like a bunch of like cracks and stuff where that or dirt where those chemicals can kind of coalesce and get together, well, you're going to end up having a bunch of false positives. Like, oh, look, there's a crack or whatever else. And really, it's just a bunch of gunk that's like grabbed those chemicals and held on to them. So that way, whenever you inspected it, it looked like there was a bunch of like birdshot holes inside the part, and that's not the case. It's just dirty. So it requires a lot of cleanliness, and if you don't clean it correctly, well, you could have false positives, and that's not necessarily anything that we want. All right, and then the direct visual detection on results is required, so you still have to use your eyeballs. And so if it's like something that is working on the inside of the airplane, you're not going to be able to dye pin it because it's on the inside of the airplane and you can't see through things, just like with the visual inspection. All right, mag particle. So the advantages of a mag particle inspection. All right, so the advantage of a mag particle inspection is it can be portable, inexpensive, sensitive to small discontinuities and immediate results. Moderate skill is required, and it detects surface and subsurface discontinuities, and it's relatively fast. All right, so under the advantage where it says it can be portable, most of the time a mag particle inspection isn't. Most of the time you're going to see a mag particle inspection done. It's going to be in some sort of big shop somewhere. What they're doing is essentially they're magnetizing the part, and they're going to take it's almost like the stuff like an Etch-a-Sketch. It's these little ferrous shavings and like this dust basically, and you're gonna drizzle it on the part, and then wherever the discontinuity or wherever the failure is inside of that part, it's going, because of the way that the structure is built, it won't let the lines of flux for that magnet go straight. Instead, there's going to be these little jogs in it, and those little jogs grab that dust and it holds onto it. So it tells you, hey, look, inside of this, like if you're inspecting a shaft and you have it in a mag particle machine, and you're dusting it on there like you would like for fingerprints or whatever, you're gonna say like, okay, inside this shaft right here somewhere there's an internal crack of failure, because otherwise all of the lines of flux would have just gone straight, and then all that dust would have gone to the end. But instead, since there's this like weird anomaly, it's grabbing the little shavings and it's staying out there. Now I'll tell you from just experience, you generally don't see mag particle out on the flight line anywhere. Where you're going to see it is going to be in like MROs or like in some sort of specialty shop, and a lot of times the part comes off and it gets shipped off to it, and if they're going to do a mag particle inspection. Because of that, they generally will try to steer away from mag particle as much as you possibly can, because you can do the same thing in other ways, and it's a lot cheaper, and you don't have to go through all that drama of doing that. But it's still possible to run in it. And so all you're really doing is just magnetizing you have like electrical current that's running through a part that anything that, and we'll find this out. This is basically the way solenoids work, but like essentially like the one you whenever you electrify something, it creates a magnetic field of that part. That magnetic field then is dependent on the underlying structure of whatever is being electrified. So if there is some sort of discontinuity in the structure, it will cause a flux in that magnetic field, and that's what the mag particle inspection is looking for. So if you have a shaft that's supposed to be like just one solid shaft, there shouldn't be any like voids in it, no cracks, no internal weirdness happening or whatever. And all of a sudden you get a bunch of like little parts of the mag particle stuff stuck on the side of the shaft. Well, then you know that like, hey, look, this isn't wrong. That's what a mag particle inspection does. But generally speaking, you won't see a whole lot of it, or at least I haven't seen a lot of it in 20 years of doing this in different places. Okay, eddy current. Eddy current you will see. Eddy currents are portable. They detect surface and subsurface discontinuities. They are moderate in speed, immediate results, sensitive to small discontinuities, thickness sensitive, and can detect many variables. All right, so an eddy current machine is like a little box and has a TV screen on it. And then you have like a little wand that has a gooseneck on the end of it, and that wand is connected to the box. And so you're holding this box almost like imagine like a portable TV, or probably better to say like almost like a multimeter. So like say you get your multimeter like box, and you have your little wand, and you go over to the area that you're inspecting, and you go back and forth really fast. And you progress on, and so you're essentially going like up and down, 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 just like that. And what's happening is that like it is sending an electrical current through the aircraft, and then as it goes over it, it says like, hey, look, I'm getting this a really good continuity through this part, but also right here I'm having some sort of like weird, fluctuation. It's gone way up, or it's gone way down, or there's some problem, and that's going to show up on the chart that the eddy current machine shows. And so like you'll see this line, and also there'll be this big spike on the graph, and you'll say like, oh look, there's something right there, and then you might, instead of going up and down, you might go side to side and come back, and you can kind of map out where that crack is at. This is a pretty common test you'll see. You have to be certified in all these different things. So like you won't be certified here, but you just have to know that these exist. And that's why we're not going into super duper detail with it. But essentially, like if you're in the airlines, you're in an MRO, you're working flying at Boeing, you're in the military, you're going to have a shop that basically that's all they do is they go around and with these NDI machines, NDT machines, and they use them based on whatever whatever the aircraft requires at that point. And so we like when we were at Boeing, we would call these guys up. They would show up, and we would say, "Hey, look, this is the area. This is the task that the maintenance manual task that says, hey, look, do an eddy current inspection from this point to this point, and from here to here." And they would go and they would do their whole thing. In the Army, this is how we would do that tail rotor inspection. That you'd have an eddy current guy come out, and his name was Rudy. Rudy would do the whole thing, and he would take his little wand and wand over the cracks, and we found cracks that way. So one of the advantage of it is being able to find cracks that are happening internally. The metal is failing, internally, and it's starting to crack and go, and then before it ever manifests on the surface, you're like, oh, okay, this is a problem, and so you can know things early on. Okay, so disadvantages for the eddy current is like surface must be accessible to probe. Rough surfaces interfere with tests. Electrically conductive materials. Skill and training are required. Time consuming for large areas. All right, so let's just kind of take these by the eases. Surface has to be accessible to the probe. So the downside with an eddy current machine is that it has to touch the thing that is being inspected. And so if you think there's a crack working on some spar that you can't get to, and they can't get their hand in there to wand it, then you can't use an eddy current inspection technique. It's just not going to work because it's required that you touch it. It's really good for like a surface structure, like that you can just stand there and hold the thing and do your deal, and that's where you'll mostly see it. You'll see it in other uses too, but the problem with a eddy current inspection is that like you have to be able to wand it, and you have to have a big enough area to where you can kind of go back and forth and actually and work. Rough surfaces interfere with the test. Same, kind of talked a little bit about with dye pen, but like essentially like what it's measuring is like the continuity of that surface or that material. So imagine let's see, like a piece of aluminum that we use for our micrometer reading. Like this would be really good with an eddy current. You can go back and forth, and like it's showing you the continuity of this block. But let's say it was super rough, you wouldn't be able to go back and forth, and even if you could, it's gonna fail every time. But because what it's showing you is the roughness of the surface. If it's a nice mirror surface, really good for eddy currents. If it's like really rough and there's a bunch of gunk on it or paint or especially cart paint, it's not gonna do you a lot of favors with the eddy current. Okay, skill and training are required. This isn't something that you can just go and do. Like whereas like with dye pen, as an A&P mechanic, you just grab your dye pen stuff and off you go. But to be legal and to be good at it, you really need to be trained and be certified with an eddy current machine, so that way you can start to separate the wheat from the chaff. Like what's really a failure, what's a bunch of noise, and what's kind of like what's just weirdness with the machine or the service that you're using. So it's something to think about. It's time consuming for large areas. So imagine, like the area that we used to inspect in the 58 was about like this, like probably about maybe like 3 by 5 inches or so. And it would take them about 10 or 15 minutes to really go over it pretty well. So now imagine if it takes like 10 or 15 minutes, 10 minutes for 5 square inch area. What happens with the with the wing of like a 777? You can be there all day just going back and forth. How many days are you going to take? Anytime you get some kind of monotonous thing like that with people, you're going to get things missed just because people like get bored, their minds wander. People are fallible, so it's probably not the best way to do something that's really really big like that. All right, okay, so ultrasonic inspections, you're going to see more and more and more of that. The more composites become like a mainstay. They are portable, they're inexpensive, they're sensitive to very small discontinuities. They have immediate results, little part preparation, and a wide range of materials and thicknesses can be inspected. Essentially, it's doing the same thing that the eddy current machine did. Instead of using electricity, it's just using sound. It's going to turn around and say like, it's going to send like a kind of sonar-ish wave, and as it goes back, it's looking to have like a uniform return. And so it's going to say there, boom, and like it's going to come back and say like, okay, well, and you won't be able to hear it or anything, but like the if the return is nice and easy, well then, or nice and uniform, then you know that everything that it just passed through is perfectly fine. Just like kind of your sonar on a boat, your depth finder. Like what all depth finder's doing is going through and saying like, hey, look, here goes a wave, and then we're expecting to see this wave come back. But if there's something in the way, say there's a fish in the way, well, it interferes with that, and then all of a sudden you get a blip on the screen. Ultrasonic inspection is basically the same thing. It's looking for if there's a crack on the inside, it's going to send off this like wave and say like, this over here sounded really really good, and this came back exactly the same. So we know these areas are good, but right here in the middle, also we got like a really fast return, and so it's like there's something not right there, something we need to look at. That's all an ultrasonic is. So it comes in, it's portable. It's like a little box and with a little probe, and you just run over the top of it, and boom, off you go. Okay, so it's a lot just like the eddy current. The disadvantages, you have to be able to touch the surface of the part that you're inspecting. So if it's something that's like buried deep in an aircraft structure, you're going to have to take a bunch of parts to get to the thing that you're going to inspect. So if the thing like a wing spar or something you're trying to inspect, with an ultrasonic inspector, you're going to have to turn around and like take a bunch of parts just to get access to so that you can do the inspection, which is not uncommon. Those things happen pretty regularly. Rough surfaces will interfere with the test. All these are very, very similar in that regard. Highly sensitive to sound beam discontinuity orientation. Okay. High degree of skill and experience are required for exposure and interpretation. So just like with the eddy current, like you're going to have to, you need to take a class on it and develop a skill set. I'll tell you, this is something that not a lot of people do, and you can make a lot of money for it in and outside of aviation, because like bridges do the same type of thing. Like big engineering firms will pay for these types of inspections, because you're saving a lot of money by simply using science rather than just taking everything apart. All right, there's two more, and we're just going to kind of I just want you to be aware of them. X-ray radiography and isotope radiography. I've never seen them used anywhere, and I would imagine that like the only places that you're going to see these things used is either in like high, like a very resource rich environment. Someplace that has a lot of money that was willing to pay a lot of money to get something inspected, but essentially all you're really doing is X-raying the part, and you're just like you would go get X-rayed, and they'd be like, oh look, you have a broken bone or cancer or whatever based on the returns from this X-ray. They're doing the same thing, but they're either using radiation or they're using actual X-rays to do it. The reason being that why you don't see it like really widely used is that it's hazardous to your health. It's very, very expensive. They're hard to move around, and yeah, you have to know what you're doing to. I mean, like you think like an X-ray technician is like a whole job field in and of itself. For people, this is no different with aircraft. It's just instead of like X-raying a person, you're X-raying a part, and you're looking for the same types of things, like little internal discontinuities. But know that you can pursue that if you would like, and you could always send out for it. I've never seen a manual call out for isotope radiography inspections. Maybe if you worked in space or something, you would run into that, but not on a flight line anywhere. The most common ones that you're gonna see, visual inspection. Everyone's gonna do that no matter what. You will see dye pin on a pretty regular basis, especially in general aviation. Dye pin is very common, but when you start to get into the bigger aircraft, eddy current ultrasonic or kind of the way that you're going to end up see. That's the most common ones you're going to see NDI'd out. Eddy current, especially ultrasonics, getting more and more popular, obviously because the presence of composites really kind of dictate the use of ultrasonic. Okay, here we have a composites demonstrating board, and we're going to do a tap test. Now, a tap test is simply just literally tapping a piece of composite to try to listen for any sort of voids, just like you would try to find a stud in the wall. It's the same concept. Bang on the wall, and eventually you hear that difference, and you're like, okay, well, here's a stud. But anybody who's ever banged on a wall before looking for a stud knows that like you might be able to bang on and hear the difference, but you're probably not like going to be able to triangulate exactly where the stud's at. A lot of times you end up drilling a hole and you miss it because the stud's only so thin, but your range that you're tapping is a lot bigger. Anyway, it's no different than a tap test. Tap test is good to try to help find something, but then you want to confirm it with a higher form of testing. Now, to conduct a tap test, all you're really going to do is take any sort of metal object and tap the composite. There's actual tapping hammers that you can buy. You don't necessarily need them. For years, this was known as the coin test because people said just take a quarter and do it. It can work. So we have our little piece of metal. We're going to sit there and we'll tap. And what we're going to do is we're going to work a grid pattern. We're going to go back and forth one way, and then we'll go up and down the other way, and eventually we'll find a void. you hear the void? Listen to it again. Hear that? Now, the void is right here, like it's right in this area. And I know it because I put it in there. This piece of composite had several holes drilled into it. I went to the back side of the hole with a scratch awl and just made a void just for this purpose. Now, if we wanted to elevate this, try to actually kind of map out the void, there's a bunch of different ways we could go about it. Most commonly, the right thing to do would be to use an ultrasonic tester to come out and do this, but we don't have an ultrasonic tester. So let's say you were on the fly line and you had to come up with a field expedient way of finding trying to map out this void. What else? What's something that you may have? Well, what we do have is a heat gun, and we have a FLIR for doing our thermal inspections. So let's use that. We're gonna look at it with the FLIR and notice that it looks fairly homogeneous, not a whole lot of differences. Take our heat gun. Let's see what happens. You'll start to see the changes in the composites on the image on the FLIR, because the different heat retention rates. So there's our void right there. Take the heat gun away. You notice how those two spots stay lit up. Reason being is those are two repairs. Okay, so we're gonna do a dye penetrant inspection. Now, a dye pen is super easy. A lot of times, guys will have them in like little kit bags, and you just go to the parts room, get whatever you need if you don't have one, and then you take your little part or wherever you're inspecting and apply your cleaner, penetrant, developer, and inside of about 15-20 minutes, your inspection is done and over with, and you know if you get a good part or not. So we're gonna walk through the steps of it. First off, we have a part, but on this part, there is gunk and grime. All right. So first thing that we're gonna have to do is get that gunk and grime off. So we're just gonna take a cloth and we're just gonna completely give it a once over, try to get as much of it as we possibly can. Then we're gonna take our cleaner that comes with the kit, spray it on the part. That will get into these cracks and stuff, and then push out any dirt or water or stuff from the cracks. So that way we have a nice open chasm to put our penetrant into. Once we have a clean part that's ready to be inspected, then we spray our penetrant on top of it. In this case, it's red, but on the board it's gonna be green because that's all I have. All right, so the penetrant will get sprayed on all over the part. All right, but inside the crack, you have the penetrant will get inside the crack as well. We're gonna let it set for about 10 minutes, and it's gonna slowly kind of seep its way in and try to find every little crack and crevice and place that that penetrant can get into. It's penetrating after all. Once it's been set for 10 minutes or so, we're gonna come back and we're gonna clean it off with water. Now you don't wanna get too crazy at this point, because what you don't want to do is force the water into the cracks and displace the penetrant and invalidate the whole inspection. So what you want to do is turn the part sideways if you can, and just lightly let the water go over it and try to just rinse off as much excess penetrant as you possibly can, and take a rag and kind of clean it up as best you can without pulling any penetrant out of any cracks and stuff, because once again you don't want to invalidate the inspection. Once it's clean, you're gonna come back with your developer, and your developer is nothing more than a chalky substance that's in aerosol form, and you're gonna spray it on top of it, kind of old school deodorant that you spray under your arm. It's the same kind of concept, just like powdered aerosols. It'll go on top, and then once that penetrant lays on top, it's going to pull out the penetrant into that white substance, and it's going to like show up in that color. In our case, it's going to be red, and the board's green. It's going to show up in that white powder, and you're going to be able to turn around and see where the cracks are at. Now, if you want to go a step beyond, is take a black light and shine it over the top of the part. That's going to essentially, the way that your eye is going to interpret that light being reflected at you, especially at an angle, you're going to turn around and see that color really pop, and you'll be able to see any cracks that are on there. On our part, we don't have a part that has an internal failure that we know of, at least yet. And so you're going to look at it and you're going to see like little bits of red and stuff like that, but it's not really, that's just a leftover dye penetrant. If you want to verify that, you could clean it off, do the inspection a second time, and you would know. But this is what it would essentially look like. If you were to look at, let's say like this is our part right here, and you're looking for the defect, it'll look like a very pronounced colored line. You'll see like little spots and specks and stuff because there's deviations in the skin of the part, and there's like little bitty leftover bits of penetrant all over the place. But an actual true blue crack, there will be no mistaking it. They're like, that is a crack for sure. Okay, another thing that we want to touch on while we're doing non-destructive testing is welds. The reason being is that a lot of times what you're actually inspecting are more welds than anything else. This is especially true with parts of an exhaust system. So here's an exhaust system off of a Continental, and you see all of the welds that happen on, like all of these welds that happen on the exhaust. And because the exhaust gets hot and it gets cold and expands and contracts over and over and over again, those are typically where you're going to use especially dye penetrant to inspect those manifolds on a reciprocating gear aircraft. Now, welds break down in the things that you want to look at is the way the arcs are in a weld. All right, now a good weld has a certain look to it, and it's not something necessarily that you could empirically measure. It just looks right, and so you'll have to kind of work that muscle and develop it by seeing a lot of different welds. And bad welds are easy to spot because they look bad. Good welds, they look nice and symmetrical, and they look like somebody intentionally built that weld to look that way. With these nice little half moons that are evenly spaced, they're not globbed up, they're not heaped up on the metal, they're not too thin. They're nice, and everything is symmetrical and in order. Now, there's three things that will cause a bad weld: speed, voltage, and current. All right, speed being probably the biggest offender of everything, where like the welder went too quickly, and so those little half moons are really elongated, or they went too slowly and they're all packed on top of each other like really tight. Either one is not what we want. Going too quickly, you don't get a good bond, and doing too quickly, you could blow the metal out. And if it didn't blow the metal out and it welded, it's probably been weakened. And it's probably a place where a fault is going to appear later on. Voltage, having the voltage set too high or too low will also impact that, as well as the current being too high or too low will impact the quality of the weld. So what you want to do is look for welds that are good, and most of the time you're not going to find a whole lot of bad welds on aircraft that are flying. Reason being is that like those welds would have been caught in the quality control processes and procedures of that certificated aircraft before it ever rolled out. However, if you get into a situation where somebody has done a lot of repair work that involved welding, then that might be something you want to look at. In either case, they are a hot spot for cracks to develop, and so that's really what you're looking for. You're inspecting the weld, but you're really inspecting to see what's around the weld to see if anything is come apart. If you needed to get something welded, you can weld yourself, and we're going to show you how to weld out here. And that's an authorized repair. It's an authorized procedure. I will tell you just from experience, I've never once seen anybody weld anything on the flight line, because welding itself is an art. And so you don't, like, you're an aircraft mechanic, be an aircraft mechanic, don't be a welder. If you need a welder, then call somebody who is good at welding and then pay them to do the thing that they're good at. Outsource it. Just go that route. But if worst case scenario, and you're the only guy in town and you have a welder and this thing needs to be re-welded, you can do that. There's nothing wrong with you welding it, and we're going to show you how to do that. But kind of the rule of thumb is that, like, if you really need something re-welded, call somebody who's a good welder. While we're on the topic of just finding cracks and things like that, there's some hot spots you want to look for in and around holes, generally bolt holes. You'll see this a lot, like on aircraft cowlings. There'll be a hole, and then there'll be a crack that comes off of, because the cowling's coming on and off, on and off, on and off, and that stress will eventually cause a crack to appear. Most all the time, it's at a 90-degree angle from the hole itself. And so you'll start to pay attention to those, and that'll be a place that you really want to pay a lot of attention to whenever you're doing your inspections. Anytime that you have a 90-degree come together, a crack will come off of that. That's something that you want to pay attention to. Any time that there's like stress or a strain of some sort of time, we're going to get into this a little bit in our structures about how to try to the different types of stresses and strains that are on an aircraft. You want to pay attention to those areas, because that's where your cracks, your nonconformities, your voids are all going to start to develop. Voids on composites are another big thing to look out for. Voids are almost always caused by water. So like you'll end up flying through a rainstorm, water sits, and where it corrodes metal, it'll cause composites to delaminate from their core material. So most of your composites are laid up where it's like you have, say, carbon fiber down here, then you have a core material of, say, foam or honeycomb or something like that, and then you have another layer on top of it. And together, that's extremely strong, but it can delaminate, it can come apart, and that's what a void is. And so water is one of the key ingredients that makes that happen. Sometimes there could be a nonconformity in the manufacturing procedure, and that just finally it takes several thousand hours for it to manifest, and now it's starting to pop off, and you might be the one to catch that. But look for voids there, and like any sort of floor, any place where there's high vibration, any place the vibration is a big one. You'll see a lot of that happen on helicopters specifically, but also on aircraft. And so you want to look at places like that. Any place where there's like high traffic, there's a lot of the same thing happening over and over again. So doors closing and opening, a lot of people walking on or off, or sitting down, standing up. Any time that there's a load on, load off, load on, load off on a regular basis, that back and forth is just stress on the machine, and the machine will manifest that stress in forms of cracks and voids and all that kind of things. But either way, so this has been your primer on like what to look for and then how to employ NDT. We're going to get into this a lot more actually on the hangar floor as we go through there and we kind of start pointing these things out. So this should just prep you so that way you understand what's going on, and then whenever you show up to the hangar, we're actually going to mature this skill set.